For our next geometric transformation, we're going to look at expansions and contractions. And the big difference in today's lesson is that congruence is not preserved. Congruence is not preserved. So we're going to have a transformation where the image is no longer going to be congruent to the pre-image of our shape of our figure. Obviously, points are always going to be ideally no dimensions, no size whatsoever, but a circle will no longer be transformed into a circle. It looks like we have a rhombus to get us started here, at least that's by appearance. We can see x prime, the image of our original x-coordinate. Multiply that by some fixed number, which we could call k. K is a real number. By the way, k could even be negative. We'll see that soon enough. But what we're seeing is, perhaps, if we had the point 1, 1 for a pre-image, what we would see is that our y-coordinate would remain the same, but for our image, if perhaps we were dealing with this x prime is 2 times x, I hope you could see very quickly that 1, 1 would be transformed to 2, 1. So there is a horizontal stretch or expansion. The y-coordinates are going to be the same. Area is no longer preserved, of course. The area of the original figure, which we would have at k equals 1, perhaps we have this rhombus, this new figure has been stretched out. And very importantly, we can see that we could write a matrix form. We can have x prime, y prime is equal to, well, it would only take a moment for you to see, hopefully, that we'd have k0 up on top, so that k would multiply to x, 0 to y. Down below our row would have 0 and a 1. So this, of course, will arrive at these two transformation equations. I must bring up, however, that we could multiply by the inverse of this transformation matrix if we wanted to solve for the matrix xy, not the primes. We'd have to multiply on the left. And that, of course, would be k0, 0, 1, and we'd have that inverse right there. And when we'd multiply by the inverse over on this left, on the right side, but multiplying on the left, you could see that our transformation matrix would just simplify. I'm bringing this up because sometimes we might deal with an abstract problem where we're just saying we're multiplying by some fixed number k. I wanted to bring up, we've been talking about the 89, that you can enter in just arbitrary variables with the alpha button. I entered in a matrix k0, 0, negative 1, raise it to the negative 1 power, and this is going to be your inverse matrix. Even though k is just written as this abstract value, arbitrary value, we can still get a transformational inverse right here. So that's going to really play a huge role down the line in our next few lessons. But look, we can also have a stretch among the y-coordinates. Obviously, it's going to be just the x-coordinates remaining the same, but the y-coordinates being multiplied by some fixed number. The transformational matrix, of course, would be 1, 0, 0, k. I hope you can see that very quickly. So once again, area would not be preserved. However, when we move down to this last scenario, you might say, well, what if there's a contraction for x and for y? And in this case, we actually are performing a stretch or a contraction if k is smaller for both coordinates. Well, once again, area is not preserved. However, we are going to have similar figures. we're going to have similar figures. It's going to definitely be the case where, you know, the image is going to be k times larger than the pre-image. And the area, if you want to remember how area always is applying with a ratio for similar figures, the area of the first figure divided by the area of the second figure, it's always going to be in the ratio of 2 sides squared. I could even say 2 segments squared. Any 2 corresponding segments would hold to this relationship. And again, this is for similar figures. But let's see what we've got here. We have several problems that we're going to jump into right now. For number 1 here in our packet, and again, let's see, we are on page 146 in our packet here. So we've got the line 3x plus 4y equals 5 is transformed by these equations. You know what? We could solve for x and for y. It's very, very simple to do that. And then, look, instead of writing 3x, we're going to replace that with 3x prime all over 2. Of course, y is replaced with y prime. And my goodness, we could even drop our primes. We may multiply both sides by 2. And if we did that, you, of course, would get 3x plus 8y equals 10. So I just did 2 things right here. I dropped the primes, and I multiplied everything by 2. Let's take a look at this number 2. The parabola y equals x squared is transformed by means of the following equations. That means x is x prime all over 3, and of course y is just y prime. As we continue here, we could just say, well, look, our y is just going to be substituted with a y prime, but our x will have x prime all over 3, and then we'll square that. We could drop our primes even, and very quickly we'd have y is equal to x squared all over 9. Okay, discussing for number 3, determine the area of the ellipse. Well, this is something to really think about. Let's go back and talk about how area was not preserved. First of all, I just want to go back up to the very first problem up here. Let's just say that we had a very simple square with a side of 1, and then we had a right angle in here. If we were to say have a transformation where our image is going to be k times our x, but our y will be exactly the same, we could see very quickly that we'd no longer have a corner point at 1, 0. We'd have a corner point at k, 0. And we'd still have that same height of 1, for example. This might lead you to believe that when you just have one transformation occurring with the coordinates only to the x coordinate, you'd say, well, it certainly appears that this dimension right here is being affected by k. So certainly we could see this area would be k and this area would be 1. You would be led to believe that our area is multiplied by k in our image. So, by the way, this would be correct. We could say that the area of the image is k times the pre-image area. And you can see why, just from this very basic rectangle compared to a square. Likewise over here, the same would be true as we were performing a transformation on y. The image area is going to be k times the pre-image area. Just imagine that we are stretching our square in the vertical direction instead, and it's exactly the same idea. However, when we come to the dual expansion, what you can see is the area of the image in this regard is both of these two quantities multiplied together is k squared times the area of the pre-image. So where does that leave us for the formula of an ellipse? I think many of you know the formula for the area of an ellipse. I think it's talked about a lot, but I'd like to give you some reason to see why this is going to be true. Obviously, an ellipse, you can envision that we are stretching a circle. Just to review, down here is 2 squared, down here is 3 squared. If we were to draw this picture, you could say, well, it's an ellipse. From the center, move 2 steps right, 2 steps left, move 3 steps up, 3 steps down. And we can see it would be an ellipse that looks something like this. Well, I guess what I really want you to see is imagine that we had that x prime is what we're dealing with working backwards. Imagine that we had x prime over 2 quantity squared plus y prime all over 3 quantity squared was equal to 1. And our original transformation, our pre-image, came from a circle where we'd say, look, x is x prime all over 2 and y is y prime all over 3. In other words, we'd have x prime, that is going to be 2 times x, and y prime would be 3 times y. You could say, okay. Well, look, the original area up here is just pi r squared. We'd have a radius of 1. But remember what we just said before up above. We'd say whatever our expansion values are, our area is going to be multiplied by those constants. So here's what we have for our pre-image. Our pre-image is going to be pi 1 squared. For our image, well, you've got your pi, that's just a pi, but we'd say, hey, multiply by 2, multiply by 3, so that would be 6 pi. So what many math team topics we'll talk about is that the area of an ellipse is actually pi a b. A is going to be that semi-axis length in the x direction. B would be the semi-axis length in the y. And of course that is always going to be true. It's true because of what we just mentioned in regard to images and pre-images. So let's see, we only have about a minute left. I'm going to make another video to continue on, but hopefully this is making sense. We'll stop for right now and pick it up again real soon.